wave optics we are going to consider. Wave optics means what? Study of light. Wave optics, study of light. Study of light in terms of waves. In terms of waves. In terms of waves. That is treating light as waves. As against ray optics. Ray optics means what? Study of light. Study of light in terms of rays. In terms of rays. Okay, of course, ray optics is a special case of wave optics. Wave optics is more general. Ray optics is a special case wherein you can neglect diffraction effects and things like that. That is called as wave optics. In this chapter, first thing we should know is this wavefront definition. Actually, what is a wavefront? It is the continuous locus of all particles or points that are vibrating in the same phase. That is called as a wavefront. So, continuous locus of what? Of all particles or points. If you consider mathematical view, you can say points that are vibrating in the same phase. So, when do you say two particles are vibrating in the same phase? Let's say there are two particles. When the two particles are vibrating exactly in tune with each other, then we say they are in phase. That is, when this reaches maximum position, this also reaches its maximum position from the mean position. Similarly, the two particles cross the mean position simultaneously. They reach the maximum in the other side simultaneously. We say these two particles are vibrating in phase. Like that, when a wave travels, the continuous locus of all particles or points that are vibrating in the same phase is called as a wavefront. So, what is an example of a wavefront? Ripples on water surface. Each ripple is in fact continuous locus of all water particles that are vibrating in the same phase. Actually, what is a ripple? Ripple is the continuous locus of all water particles that have risen above the water surface. Of course, they will go down also after a while, but before that. Okay, for example, you see this is here. Okay, this is a ripple. Here all the water particles are vibrating in the same phase. Okay, I just take the different color. Okay, this is all the particles vibrating in the same phase. So this is a wavefront. Similarly, in this wavefront also, all particles are vibrating in the same phase. So this is another wavefront. This is the first wavefront, this is the second wavefront in our order. Okay. So this is a wavefront. What is a wavefront? Continuous locus of what? Of all particles or points. When do you say points? If you want to give the picture of mathematical ideas, you can say that it is a point that are vibrating in the same phase. That means they don't have time gap. When this reaches maximum, simultaneously this reaches maximum. That means they are vibrating together in unison with respect to each other. Then we say the two particles are vibrating in phase. That is, phase difference can be taken to be 0. Okay, or even you can say the next one we are going to consider here. Rays are perpendicular to wavefronts, because we already studied ray optics. Now we are going to study wave optics. So there should be a link between these two. That is, rays are perpendicular to wavefront. If you know how to draw ray diagram, easily you can draw wavefront diagram. For this, what is the clue? The clue or the guideline is rays are perpendicular to wavefronts. Say this is a ray. Okay, meaning this is a direction in which the wave propagates. This is the direction in which the energy travels, energy of light travels. So the rays are perpendicular to wavefront. So if you draw the ray, if you want to draw corresponding wavefront, you draw a perpendicular. Okay, this is a wavefront. Okay, or this is a ray, this is a wavefront, this is perpendicular. So this is a ray. Generally we don't put any arrows for the ray. Arrow will indicate the direction in which the light travels. So we simply draw like this. This is a wavefront, this is a ray. So rays are perpendicular to wavefronts and represent the direction in which the wave propagates. Okay, that is about the link between a ray and a wavefront. Using this, you can construct the wavefront diagram given the ray diagram. Is it clear? Now the shape of the wavefront depends on the shape of the source. That is very important. The shape of the wavefront, okay, is the shape of the wavefront depends on the shape of the source. Suppose the source is a point source. Source is a point source. Then the wavefront will be spherical. If the source is an extended source or a line source, the wavefront will be cylindrical as shown here. You see, this is the point source. These are the rays. This is the wavefront. This is the wavefront. Similarly, if it is a line source or extended source, this one is extended source. Okay, this one is the extended source here, or line source, linear source. Then this is the wavefront, cylindrical wavefront. But when you observe it from a large distance, both the wavefronts approximate to plane wavefront. Whether it be spherical wavefront or cylindrical wavefront, when you observe it from a very large distance, it can be taken to be a plane wavefront. See, suppose if this is a spherical wavefront for a point source. Imagine as you go away, you can consider it as a plane wavefront. Any part of the spherical wavefront, provided you observe it from a long distance, you can take it as a plane wavefront. This is the plane wavefront. Here also, the angle between the two should be 90. Right? So this is about the link between, or the connection between a ray and a wavefront. Now we can easily draw wavefront diagrams. So you can see here wavefronts representing a parallel beam of light. How does it look? It looks like this. These are all rays. This is one wavefront. I have shown only two wavefronts here. This is another wavefront. So wavefronts representing a parallel beam of light. So this is all parallel beam of light. All these things. Parallel beam of light. These two are wavefront. They are plane wavefront. These wavefronts are planar. Next one is converging wavefront. We will see how to draw the converging wavefront. But bear in mind, whenever you draw wavefront, and the wavefront should be drawn in such a way that rays are perpendicular to it. You can see this. This is all converging wavefront. Okay, this is converging wavefront. The green color one, you know, these are all wavefront. These are all rays. The rays are converging. So first you draw converging rays, then you draw the wavefront diagrams in such a way that the wavefronts are perpendicular to the rays at all relevant points here. Okay, so this is the convergent wavefront or converging wavefront. And one more thing, there is a short way to represent all this. Short way to represent all this. For example, here. This is a short form of this. See, these two are rays, parallel beam. Okay, this is the wavefront. This is a short form. It is also used. Similarly, here converging wavefront. You can draw like this. So this is the converging wavefront. This is the converging wavefront. These two are rays. Bearing the arrows, they are rays. So next example, we see diverging wavefront. This is a diverging wavefront. You see, they look similar. They look similar. Only thing, arrows are drawn other way around. That's all. Here also, these angles are all 90. This is a converging point. Okay. You can consider it as P or F, anything. So this is diverging wavefront. Short form, if you want. This will be the short forms. Just ignore this. Okay. This is the diverging wavefront. Look at the arrows. This is the wavefront part. These are the ray side. So we have seen three cases: parallel beam of light and shortcut, converging beam of light, the short form, diverging beam of light, and the short form. In all these cases, we have represented the wavefront diagram. Understood that? Next one. Parallel beam of light passing through a prism. We see how to represent. Now, this is parallel beam of light passing through a prism. You should be knowing that this is the prism. Parallel beam of light passing through the prism. It will pass through the prism. It will come like this. Okay. So this is the wavefront. It's written there. So this is the wavefront. So that this is 90 degree here. Here also 90 degree here. So wavefronts and rays should be making an angle of 90 degrees. Now here one important thing you have to understand. According to Newton's corpuscular theory, what is so special about it? It says speed of light. This is Newton's corpuscular theory. Speed of light is more in denser medium. Note that this is according to Newton's corpuscular theory, right? But this is not true. Newton's corpuscular theory says speed of light in a denser medium is more, but that is not correct. We need not go into the details of Newton's corpuscular theory here, but please note that according to Newton, the speed of light is more in a denser medium. But that is not correct, because later on, when experimental methods were developed to study the speed of light in various media, it was proved that the speed of light in a denser medium is in fact less. So this one by Newton is not all that correct. Is not correct. Because later on, when people or scientists determine speed of light experimentally, they found that it is other way around. Speed of light in a denser medium is less. But this fact can be proved by this wavefront diagram, which is very important. You see this. This is the wavefront now. You can call it as, say, D. BD incident wavefront. It travels through the prism and comes as emergent wavefront, CE. That means by the time B reaches C, by the time the point B reaches C, you can take it as moving points on the wavefront. By the time B reaches C, D reaches E. But D travels greater distance in free space. This B travels the shortest distance in free space or in the medium. D travels greatest distance in free space. This point B travels maximum distance in medium. So greater distance, lesser distance. So here more speed is required. So in air, more speed. In medium, less speed. This was experimentally found to be true. Understood that? Very important. According to Newton's corpuscular theory, speed of light is more in a denser medium, but that is not correct. When later on the speed of light in various media were determined experimentally, it was found that in a denser medium speed of light is less. This fact can be proved by this wavefront diagram. By the time the point B in the incident wavefront travels to C, the point D in the incident wavefront has to travel to the point E. This travels maximum distance, but mostly in air. This travels maximum distance in the medium. Because distance is less, here distance is less, here distance is more. So more, the speed should be more. Because distance is more, speed should be more. Because by the time B reaches C, D has to reach to E. So from the wavefront diagram, we understand the concept. Speed of light is less in a denser medium. Okay, that is another advantage of the wavefront diagram. Now, parallel beam of light passing through a convex lens, assuming source at infinity. Of course, parallel beam means you can take sources infinity. This is the ray. Okay, converging, say at the principal focus. This is lens. See, this coloring and all just for the diagram sake. Don't take this to be the colors in reality. Okay. Now these are the wavefronts. Wavefronts. Okay, this is a wavefront. I write WF to represent wavefront. This is representing parallel beam of light. These wavefronts correspond to parallel beam of light, but these wavefronts correspond to converging beam of light. So if you want, you can draw this in short form. Let's say this is convex lens. Incident parallel beam of light will be like this. Let me remove that. Okay. Incident parallel beam of light. This is a kind of short form to this. But also you can even draw this for same thing for diverging beam of light passing through a convex lens. Source at the principal focus. Now here there is source. These are the rays. You can make a parallel beam of light by keeping the source at, say, the principal focus. Divergent ray, here parallel beam. So this is divergent wavefront. This represents parallel wavefront. So short form, convex lens, divergent beam, like this. Then you will have parallel beam. This will be the short form. I just change the color of the ink. Otherwise you will feel bored. Okay, you should know how to proceed. The next one is, I'll go to the other one. Parallel beam of light passing through concave lens. So this is concave lens, parallel beam of rays. This produces divergent beam after refraction. Okay, this is, as you all know, this should be concave lens. This means concave lens. you are asked to draw wavefront diagram. So initial wavefront is like this. Okay, perpendicular, perpendicular, here perpendicular, in all such points. So if you want to draw this short form or something, concave lens, okay, divergent beam, no? So right, you can draw like this, divergent beam, right? So this is a short form. Similarly, parallel beam of light incident on a concave mirror. So okay, this is the parallel beam, incident, draw perpendiculars, then the gray gets reflected. Because concave mirror, I have to kind of shade it this side, shade the mirror like this. Then this will be the principal focus, 90, 90, 90 and 90. So again, if you want to have a short form, incident parallel beam, concave mirror, then you will have convergent beam here. Is incident, reflected. So there is reflection to be considered because concave mirror, so we have to consider reflection.